All right. So we're getting started, and we will talk today about Schur's lemma. So Schur's lemma is important for groups, okay? And a group is not really what we are used to in physics sometimes. So I was thinking that maybe I will mention a couple of examples. So to give an example, you could say that a group in physics is that you have a sphere, and here you have some vector on the sphere. That would be our maybe block sphere. So it's pointing to somewhere to this point. And then you can rotate that point on the sphere somewhere. Yeah. And then you would say this is some composition of rotations, and we have this physical operation and so on. In mathematics, we speak of abstract groups. So I'm writing down abstract. I don't know if there's a Wikipedia article for abstract groups. I think maybe this article is actually referred to for abstract groups. And an abstract group will be a set and an operation. So let's give a star. And that's a group together. So it doesn't always have a meaning, okay? It doesn't always have a very intuitive meaning. But if you have a set and there's an operation which behaves according to the abstract group axioms, then you give some interpretation to your operation, okay? So the definition of an abstract group is just a group. So you have a non-empty set with a binary operation, maybe a multiplication, and it's a generalization of multiplication, okay? And it combines any two elements from that set into another element in that set, such that there are the axioms, okay? So associativity is actually quite important. It's fairly simple, but you know, sometimes you might not have a group structure because of losing that axiom. So what does it mean is that on physically, if I rotate here and I rotate here, then I could also, so let's say I have 3 rotations. So I rotate down, I rotate here, and I rotate up. So I could rotate both here, which gives me a rotation to this point and connect with here. Or I could connect with here and do the 2 rotations together, okay? So it's a statement about 3 operations, how they can be composed together. And why this associativity is important is because I could call A, B, another element D, and B, C, I could call E, okay? E is actually a bad, I hesitated. E is actually a bad notation because E is reserved for the identity element. So we will put F here, okay? Which means that here I will have D times C is equals to 8 times F, yeah? And it just means that you can combine those elements together in an order that you wish, but when you are combining them, you again get something from the group, from the set G, okay? So a group is a set with an operation where the operation doesn't mess it up, okay? If I take a set 1, 2, and my operation is just the arithmetical addition, then that could be a group G, okay? But if I just keep adding it, I put 1 plus 2, where this is arithmetical addition, which is 3, which is not in the set G. So that's my set G. This is curly G as a group, okay? So that operation needs to be closed under addition, okay? And to fix this, you would consider addition modulo 2. So 3 modulo 2 is equals to 1, which means if I get 1 plus 2 is 1. Okay? Stuff like that. In this case, normally we would use notation 0 plus 0, 1. and then I would be adding 0 plus 1 is 1, but 1 plus 1 I can also add is 2, but modulo 2 is 0, okay? So basically you can swap around the elements that way. And this would be a group called Z2. You will find this for sure. For sure, you will find this in the examples of this Wikipedia page on groups. Okay, so associativity is related to this part of the definition, to form an element of G. As I said, 1 plus 2 is 3. If my set is 1, 2, not 3, a nice bracket here, 1, 2, then basically this is not in my set G anymore. Okay, and then to fix it you can consider modulo 2 or so on, but yeah, so that's associativity. Identity is important. And yeah, so every group has to have an identity element. Okay, so if you discuss groups you can talk about this a little bit more, but this is easy enough. And then we have the inverse element, which is actually a very powerful property. Okay, so for example, real numbers, are they a group? They are not a group, but if you take real numbers without a 0, then they are a group, because if I take 3.14, then the inverse of this is 1 over arithmetically 3.14, and that's my inverse element. If I take a 0, then 0 to minus 1 is some sort of infinity, it's not defined, okay? So real numbers with 0 are not a group, real numbers without 0 are a group, okay? That's one example. A better example is I take a unitary operation, which is e to ith, and the inverse of this unitary operation is minus ith. Easy. Okay, so this is quite nice because this is then invertible and unitary operations form a group. As a homework, I would suggest that you consider this abstract group definition and write out what is the set for the unitary group. And then write out what is the binary operation. Binary operation means you take the set twice and you get a new element from the set, okay? If you look up some textbook or lecture notes available on the internet on abstract groups, first semesters of mathematics studies in undergrad, then you will see actually people specifying that the dot is actually a map. So you could also write f here and would be a function, and a function f takes g prime and gives you g prime in G. Okay, so that's roughly groups. So those groups are very abstract and you just say like you can combine things together. Okay, and now the point is that there is something which is closer to what we are doing in physics, which is called group representations. Okay, I will write it down. Group representation. And a group representation is a subset, so let me write G, of the GLN matrices, which means those are invertible matrices, okay? So we directly specify that we will be working with invertible matrices, and it's kind of lucky that I'm writing it here because I was stressing that this inverse element is quite a powerful property because it makes groups into very nice structures, but then not everything can be a group because you sometimes cannot invert. So to give you one example, what matrix I cannot invert a projection measurement onto spin down. Okay, why cannot I invert it? Because 0 to power minus 1 is, I don't know, right? So this matrix is not invertible. To know whether a matrix is invertible, you have the determinant of the matrix A criterion, which should be non-zero. So this is all A matrices n by n, such that such that the determinant of this matrix is non-zero, and this is our group here. It's actually a group of general linear transformations. Okay, so those matrices you can view both as an abstract group and as a representation of itself. Okay, so I don't have time to go through all this stuff, but if you look here at group homomorphisms, then a group representation is a special group homomorphism from the group into general linear matrices. Okay, which basically means that the multiplication of the matrices is giving you basically the same operations of okay, I will talk about the homomorphism a little bit. Okay, so let me consider Z2. So if I don't mess it up, Z2 curly Z2 will be the set 0 and 1, and then will be addition mod 2. This is addition mod 2, and that's basically a pair of taking the set. I take the set and I take the operation. That's this abstract group. So let's see. First of all, 0 is in my group Z2. So I can take 0 plus 0, mod 2 is 0. Then I can take 0 plus 1. It's an abelian group, which means this addition is symmetric with exchange. I get 1, and 1 plus 1 we computed is 0. Okay, so that's a representation of Z2. So now, so that's an abstract group where I had just a set of symbols and I had this. So I could also write A, comma B, just two symbols. I don't know what they are. And I have my my plus A, comma B addition. That's some addition. Or I will write here some map F. Okay, that will be an abstract group in the sense that I will say f of A, comma A is A, f of A, comma B is f of B, comma A is B, and f of B, comma B is A. Okay, that would be a homomorphism between those two groups. It's a trivial homomorphism because I just can identify A with 0 and B with 1, yeah? But this is an example of a homomorphism. So basically, instead of doing the addition here, so I have two groups with two different operations, dot and star. So first of all, I will do the operation on A, B elements of my group G with the dot, and then apply the mapping to map it from G to H. And then what I can do is I can take the element of the group. So here I took phi of C. I can take this element and can get this element. Both gives me elements of H, and then I combine this with that. And what we are saying here is that it should be the same. Okay? Good. I hope that this is something you can follow. So now I wrote down a trivial homomorphism from our group Z2. Okay? So let's check what happens if I have the set of matrices identity. Okay, maybe I will even spell it out. 1, 1, 0, 0, and 1, minus 1, 0. And the matrix multiplication. Okay. So that's a group that's bridging tutorials curly B. Okay. So what's going on? Let's see. Let me do the computation. So I take the first element, I will call it A, or I will call this A and B. We know those matrices. This is the identity matrix and the Pauli Z matrix. But let me combine A times A. This is identity times identity, as matrix multiplication gives me an identity. A times B is identity times Z. It's all commutative here. Z times identity, clearly I can do this, gives me Z, which is B. And now if I take B times B, this is our operation 1 minus 1, 0 squared. We see that this is 1 and minus 1 squared. And that's identity, which is A. Okay, so let's look at this. Our operation applied to A and A should give me an A. My operation is matrix multiplication. A times A gives me identity, which is A. So first combination correct. F of AB should be equal to FBA should give me B. So AB is equals to BA gives me B. Okay, and here I actually computed it for you. B times B is our operation BB should give me A. Okay, so what I constructed here is a homomorphism between the group Z2 because there's a one-to-one correspondence between the elements. Okay, so my phi of A is A and phi of B is B. Okay, good. So nothing in the chat so far. I think that's fairly clear, which means this association that basically I take the element A, which is 0, and I associate to that element A the matrix identity, and I take the element B, which is 1, and I associate to it Pauli Z. That is a mapping between our abstract group Z2 and a subset of invertible matrices, okay? Which means this is a group representation of the Z2 group, okay? Because if you find a homomorphism from an abstract group into those general linear matrices, you found a representation, okay? So now instead of doing this multiplication modulo 2, the way I did this, the way your processor on your computer does it, instead of that, I could be doing matrix multiplications and then go back. Okay, that's what I was doing here on the bottom. This was the second check, that was the third check. We check that all of them are the same. Okay, so that is a group representation. We have abstract groups, which is just say, I have those elements and I can combine them in those ways. So A times B will be this element, C times A will be that element, and so on. Each element has to have an inverse, there's an identity, and then you can combine them in different ways, okay? And that would be an abstract group. If you find a way of implementing that using matrix multiplications, okay, then you found a group representation. Good? So today we will talk about group averaging, which is very useful and so on. And that is actually useful for group representations, okay? This is a tutorial also showing a bit about research. So I found here a really good thesis by Jonas Haferkamp. And he's really a wizard of all this stuff, like a rising star of using representations to get physics results. So you can have a look how a really, really good PhD thesis looks like for somebody who actually did a lot of abstract pure mathematics before. So that would be mathematical physics here, yeah? And Jonas is using all of this stuff from group theory to derive physics results. So, for example, considering quantum advantage for some Hamiltonian dynamics, you can use probably some group theory here. Linear growth of quantum circuit complexity, this is all group theory. Unitary designs, this is a big subject in mathematical physics in quantum information theory. And all this stuff is based on, isn't this just Schur's lemma? Okay, and we are talking about this. So we will discuss this more for physics and so on, but this is just to say that if you look up this thesis, you can, I will link it later. If you look up Jonas Haferkamp and thesis, that's how I found this Jonas here. Okay, and then you can have a look, and we will look at the representations. So what I was more or less saying is repeated here. A unitary representation of an abstract group G is a tuple rho and V, where V is a Hilbert space, so it will be some matrix space. And rho is a mapping of elements from G to elements to unitary matrices on that Hilbert space. Okay, so it's twisting around a little bit. I was talking about general linear matrices, but if you define a representation with this general linear matrices, you can prove that it will be unitary. Jonas is considering a Hilbert space, so the state space of quantum systems, and then he says that it should be mapping into unitary matrices directly by definition. It's more or less the same. So you have this continuous map from the group G to the group of unitary operations on V, such that it is a homomorphism. Okay, why do we see that it's a homomorphism? Because the group of unitary matrices is just matrix multiplication. So here we are applying this H star like we were doing on Wikipedia. So let's look. On Wikipedia we had this. So there's rho times rho is the right hand side of this equation, and on the left hand side we need to apply rho to the composition of the elements. Okay, and this abstract group G, probably there's some notation before, the multiplication here is just this kind of dot product here. Okay, so for any two elements of this group it should happen, and we should have soundness, so the identity element should map to the identity element here. And it's explained the identity element, we talked about this. And the sub-representation is something where you have a subgroup. Okay, great. And then later you can scroll down and you will have Schur's lemma as theorem 1. In mathematics, sometimes you say lemma is a helper result, and that's true with Schur's lemma. That's why the title of this nice chapter here, isn't this just Schur's lemma? It is a lemma because Schur used it to prove orthogonality of characters and so on. At some point, maybe we will discuss this. But here is the theorem because it's so powerful. Okay. Jonas is using a word intertwiner, which is probably defined in one of the definitions. Before I go away, we will do something simpler. This intertwiner stuff you will also find somewhere here. Intertwining maps, you have all the stuff on Wikipedia, of course, but this is for Lie groups and Lie algebras. Today I want to talk about simpler stuff. So today I want to be talking about this. I had to tell you all about representations, because now we can understand the statement. And what I want to show to you is, where is my writing device? Okay. So I want to show you this equation. And actually, we are more interested in the case where there are two spaces. So, okay, there was some notation. This is a bit more general than we needed. It's talking about two different representations and the mapping between them. We will be now putting always V equals to V. So rho W is rho V, which is for us rho. So if I rewrite this formula, I will have some element H0, 1 divided by G. and then I'm summing G over the group, and then I have a row of element G minus 1 H, a row of G. That's our formula. Okay, and the statement is that because they are equal and finite dimensional, this will be 1 divided by trace of H. Okay, quite a magic formula, but we can understand this. Yeah, so I don't know if I should tell you about what we are skipping. So the notation is just above it. It's a more linear algebraic definition. So we have two irreducible representations of some group on two different spaces, and then this H has to be a mapping, a linear mapping of V into V, and then this is this, well, what we have here. But we can make it simpler and understand it a little bit more. So let me define H. Let me take a 2 by 2 matrix A, B, C, D, and call this one H. And my group will be my group G will be Z2. So my set G will be two matrices. So I will have 1 over 2. And then one matrix will be identity minus 1. And you can think about what that would be. H plus Z minus 1 H Z. Okay. Good. So that's basically the formula. And the point is that if the definitions are satisfied, then this H0 has to be trace of H divided by 2, because n is the dimension of V, and this is 2 for us. Okay. So let's see whether that works. I think in this case it doesn't work because maybe we have something about irreducible representations or something like this. So we will check in a moment. But yeah, anyway, when we have an A, B, C, D matrix, and let's say this is actually a symmetrical matrix. So here B star. Then I can write this matrix as, what can I write it as? Basically, we can expand in the basis. So trace this matrix. So I will get A plus D divided by 2 identity plus a real part of B will give me times the X Pauli matrix, imaginary part of B times I with a minus, I think, no, with a plus, times Y plus A minus D divided by 2, if I'm not mistaken, and Z. So I can decompose this. And I'm doing this to show you what's happening in this construction of Schur's lemma. And what we will go back to is this proof here. Okay, but first I want to show you an explicit example what happens. So, okay, let me consider H to, so you see that here this is a linear transformation. So let's consider X. H is equals to X. What happens in this case? A special case of assigning A, B, C, D in such a way that H is equals to X. I will consider 1/2 of identity minus 1 times H. This is just this matrix X plus Z minus 1 is Z. You can check Z, X, Z. Okay. So what am I getting? Z times X times Z is actually, we can check in a moment, 1/2 X minus X, and it gives me 0. Okay. And why is it 0? Because I can check that the trace of the X matrix is 0. Okay. So this is maybe more or less correct. And why is it interesting? Okay. I have found a way of annihilating the X matrix. And what I actually applied to it is a quantum channel called the dephasing channel. And basically, after I applied this Schur's lemma operation to the matrix X, which is matrix H here, I got H0, which is supposed to be proportional to the identity times the trace of this matrix, but because X doesn't have a trace, I got a 0. And this operation is called dephasing, because if I would consider an evolution to some time t with X, okay, and I would interlace this evolution with my Z operation, and then I again take this evolution with X, then I will get e to it z x z e to it x, but because you should be able to check it yourself, z x z, if nothing else, just do the multiplication, I should get minus x here, which means I get e to minus itx times itx, which is identity. Okay, so if I have an evolution on my block sphere along of the equator, or no, in this case, we are rotating around Pauli X, so we are rotating along of this great circle here. So block sphere like this, Z, X, this is X, and we are rotating here in the direction of Y, okay? I would like to be rotating my qubit like this, okay? But if I do this rotation and at equal amounts of time, I flip that rotation. So let's say I rotated until here, and now I flip until here and rotate again, okay? And flip again. So I drew it maybe wrongly. But the thing that I should get is I started from here, I should go back here. That's what we computed here. Okay. One thing to note, to do this carefully, okay? This is some sort of exercises that you should be doing carefully. If I have, this is actually important to do it properly, itxz. Then I used itzx z. This is more general. If I have unitary matrix and e to ita, then again a unitary matrix with a dagger. Z is self-inverse, so I have the dagger there. Then we can use the series representation ita 2 power n factorial u dagger. And you can see that here you will have itn divided by n factorial, then u a n times a u dagger, and then here you insert identity u dagger u, and then you have again u, which means that this becomes a series of it u a u dagger divided by n factorial. And this series is the exponential series of it u a u dagger. Okay, that's important. This is a lemma. You should write this lemma in your notebook. Study this kind of stuff. Do this carefully yourself. I'm inserting here u dagger is identity. Okay, do it carefully yourself. Good. This is fine. So we use this here. Verify for yourself that Z is unitary. Z inverse is Z dagger. Check it yourself on the matrix, 2x2 matrix. It's cheap. This is good. Which means we have ZXZ here. And then you can check that XZ is equals to minus ZX. And because it's inverse, I can put ZXZ here and I get minus X, okay? stuff like this. Those are some quick computations. But long story short, we are inverting the evolution of X. Yeah, we inverted the evolution of X. And so if I interlace a short evolution with X with a sudden flip of the phase in Z, if I do this regularly, what I get is zero evolution. Okay. So how do we go from Schur's lemma to switching off the dynamics? Well, because there are papers in physics about switching off dynamics, and it's written by people who knew Schur's lemma. Okay, so I'm telling you about some physics application here, and let me maybe recap a little bit. So Schur's lemma means that you are taking your matrices, your group representation, and you're summing over all matrices that you have. In this case, we are doing Z2, so we have two matrices. Okay, and so you will be taking your matrix and applying nothing to it, plus Z plus Z, plus conjugation by Z. So you can view this as some sort of averaging over our group Z2. Okay, and if we do this kind of averaging, we are averaging it down to identity. Okay, and now when we are averaging it down to an identity, we are removing most of that matrix away. So basically, averaging over a group removes a lot of stuff. Yeah, and that means that groups are kind of spanning some distribution, and instead of averaging over time, a cosine or something like this, in matrices we are averaging over representations of groups. What I wrote down here is really my best effort to simplify this difficult formula here as much as I can. And we took the simplest group representation that we can have, which is identity and Pauli Z. Okay. So now if you apply this to any matrix, you get something. But as I was scribbling here, any symmetrical Hermitian matrix can be decomposed as a summation of Pauli matrices, like this. Okay. And I gave you one example. What happens if my matrix is X? Then I have XZ, X minus X0, okay? And now I was explaining what's the meaning of this getting zero, because you can put those generators together and you get 1 to power 0, which is 1, okay? And that's why we are able to switch off the dynamics. And this technique is called dynamical decoupling. Decoupling. Okay, there's very good papers by the group of Leader. Yeah, if you Google this, you will have contemporary papers on this. Maybe I will add some links. Good. So this is averaging over a group, and this averaging over the group allows us to remove stuff. Why is this nice? It's nice because I could apply operations from a certain group, and I could apply them as my evolution is running in the lab. And what I will be doing is approximating this relation here, where I'm switching off the dynamics, which means all this stuff, this complicated looking stuff about abstract algebra here, derived by Isai Schur, more than 100 years ago, yeah? This allows us to know which operations to run in the lab. So basically this stuff is guidance to compile quantum something, right? So if I want to write, if I want quantum algorithm to switch off dynamics, then I wouldn't know how to do it. But this is a very magical formula. You know, I was showing you that thesis, isn't it all Schur's lemma? Everything in representation theory is usually Schur's lemma. It's surprisingly powerful, okay? And now you could view those papers that I'm not showing you. They will be linked in the paper later, in the recording later. So those papers on dynamical decoupling. You can view dynamical decoupling as a corollary to abstract group representations. It's some of the best pure mathematics, but so many applications, you know? Good. Going back to our discussion. Let's complete the discussion. So now Schur's lemma allows me to get a guess what to do with some quantum. If I want to remove some matrices in some way, then I can choose a group and average over the group. What does it mean to average over the group? I will take all elements from the set in the group. I will consider the inverse element of the group and the representation of that. Take my matrix H and take the representation of the group matrix here. Okay. So in this case, our set G was identity and Z. And I showed you what happens if I apply this dephasing channel to matrix X. Now we can check, we can do the same transformation to the matrix Y. So I will have 1/2 Y plus Z, Y, Z. But if you do the same Pauli algebra, you will get that this is 1/2 Y minus Y, which gives me 0. Which you can check is proportional to trace of Y. Now, what happens if I have Z? So I will consider 1/2 Z plus Z, not Y, Z, Z. And this gives me 1/2 times 2 times Z. So I get Z. So what's going on here? Well, this is not the identity times any alpha, okay? So we need to have a look here. Normally, what we should get is that this averaging over Z should give me the identity, okay? But under the same notation of the previous over an algebraically closed set and so on, under the same notation, which means under the same statements, if they are irreducible representations of some group G. Okay, so if they are reducible, then it doesn't work. Okay, and in this case, basically I'm averaging here over the group my operation Z, but I'm already in the group, so yeah, so I'm getting Z here instead of the identity, but this is fine. So the mapping, when we choose Z to be identity and Pauli Z, so that's curly Z2, and that's our representation. That's a way of removing off diagonal transformations, because X goes to 0, Y goes to 0, Z goes to Z, and identity goes to identity. So those two are diagonal, and those two are off diagonal. So we saw that if I had the evolution ITX, Z, e to ITX, then this is approximately, I mean, I was doing it with equalities by doing another trick, but you could view it as ZX plus X IT, right? This is doing Trotter-Suzuki decomposition plus O of T squared, and we were deriving how to get this error bar here, right? Actually, in this case, this is with equality, but this is a special case calculation. In general, we don't have this. And in this case, this is identity. This full matrix becomes identity. So now what I want to still discuss is if I have H, which is A identity plus BZ plus CX plus DY. Okay. If I do ITH, Z, ITH, Z, okay, I will get ITH, and then I will get IT, A identity plus BZ minus CX minus DY, okay. Now I have two possibly non-commuting operators, so it's really an approximation here. Let me put the whiteboard. So, okay. So I need to write CX plus, the point is that it's minus DY. And approximately I can put them together. So I have E2I identity plus BZ plus CX plus DY plus I identity. Next you think BZ, which is correct. And next you think what? Minus CX. And then looking back, minus DY. Okay. And what do I get? I get a nice cancellation here. Cancellation. Okay, that's the physical interpretation that we are rotating away, which means that I get twice ITA identity plus BZ plus O of T squared. Fine. Okay. Happy? Everybody should be happy with this. Note the approximation sign because this doesn't need to commute with that, which means that we might be doing it very frequently at short times, but up to a small error when we put them together, it's then using ITA, ITB is approximately ITA plus B plus some operator which has non-bounded by OT squared. Right? That's how it went. Okay. So this A plus B is this addition here, but because I'm flipping those signs, I will be canceling this with that. That's the point of those Z flips here. Okay. Oops, there was a question in the chat. Why is U dagger U substituted into powers n times? Okay. So there was a question previously. I'm not seeing the chat when I'm. So again, for exponentials, going back, exponentials of an operator A is A to power n divided by n factorial. If I consider U exp a U dagger, then in the beginning you have only two U's outside of the series. But if you use U dagger U identity, you can consider U times A, and then you insert them here. You have the two from outside, and then you split it, obtaining a series of U A, U dagger, and n factorial. Okay. I'm not writing more because that's your exercise in the end to convince yourself what this means. Or okay, I will finish this to say that this is the exponential of the rotated matrix. So the rotation of an exponential is the exponential of the rotation. Yeah, and that's why here we are getting this Z acting on the generator. This is in general non-linear, It's only because you have the unitarity property. Only unitary matrices do that to exponentials. Okay? Good. Okay.